0x. Okay, so what we need to do? So for this instruction, so line number. So this is okay 1. So for that, what do we need to do? Trap what? 0x what? 2 3. So it means the R0 contain what? R0 contain the ASCII value of the character. R0 not contain ASCII value of the character. Now we are comparing CH with A. Okay, then we need to define some ASCII value. So we need to have, so okay, please remember, now we can say minus 65. Why? Because the ASCII value of A is what? 65. What we need to store? Minus, because we need to do what? R0 minus 60. We need to compute R0 minus 65. So then we need minus 65. So then you will say, okay, now what do we need to do? Add R2, R1, maybe R1. Can use any division. R1,
Yes, we need to load the.
R0.
We need to load it.
Yes. Very good. LD, R1 minus 65. Then add, we can reuse the same number, same register. Because we have to reuse the minimize number. Add R1 what? R0. So it will be R0 minus 65. And then if the condition is true, so this is my line, okay, now this is not line number 2. This is my line number 2. This is line number 2. Line 1, line 2. So this is line 1 and line 2 both. LD, this is my line number 3. Line number 4, line number 5, line number 6. Then we have line L1, L2, then what we are going to do LD, so this is line number 3 now. And add R1, R1. If the condition is true, BRZ, what we need to write, help me. If the condition is true, we go to L4. If it's false, L5. So L5 is here. We go to L5 or L6 because you know after S, and then we see out F. But for see out F, we need to move F where? Into R0. So basically, what we can say, okay, the ASCII value of F, if you want to have the ASCII value of F, you do not need to do the ASCII value. You can just put it like F here. Either you can compute it, what is A 65, B 66, C 67, D 68, E 69, F 70. Either you can store 70 here, or you just put this thing. So you do not need to memorize the ASCII value of F, you just put a character, it will automatically put F. So for me, this solution is also correct. Or either you put 70 here, no problem. Both solutions are correct. Okay, now then we need to load this F where? R0. LD. R0 what? ASCII F. And then we need to display it. What we need to do? Trap 0x. 2 1. And then after this the program is khalas. Exit. Trap. No, but before that, so we can do the exit here. Exit is trap 0x25. So trap after trap 0x, so we can say BRNCP exit. But at least we didn't implement what? L4. So L4 is here. So then we say LD. Now I can do it very efficiently. Anyone Instead of doing that, I can do a trick. Please remember, this is now a trick. Please think of the trick. F. What is after F? G, H, I, J. What we need? Okay, J. I'm J. Okay, J is stored where? Sorry. Okay. F is okay. F is now stored where? R0. F is now stored in R0. Now we want to store J. What is the difference? Plus 1, plus 2, plus 3, plus 4. So please remember, I can also have the ASCII value of J here, but I have to do the load. Instead of doing that, what I need to do? I want to minimize the number of instructions. Add what? R0, R0, hash 4. Yes.
Professor, if the condition is true, it will skip L5, so it will not load R0 with the ASCII value of F.
Which one?
If the condition of the if statement is true, it will skip L5, so it will not load
Yeah.
ASCII value of F.
Yeah, you're right. No. But the value of R0 is in which line?
L5.
L2?
You can add 9 instead. You go from A directly to J.
Okay, no, please. Now what we can do? Okay, please remember. Oh, now what we can do? We can use another register. Instead of writing R0, type 0x21. So then display R0. The display R0. So okay, then we need to LD R0 F ASCII F type 0x21. Yeah, you're right. You're right. We cannot do that. But because if no. No, still.
Yeah, but we need to add more.
No, we do not need it. If CH is equal to A, we are comparing.
Yeah,
So when we are comparing, if CH is if it's not there,
then it will go to L5.
yeah, it will go to L5. You're right. So then what we can do? Sorry, I'm not doing that. What do you need to do? LD?
If I say you can add 9
Yeah, we
instead.
can add more.
You can
Because,
It's already at A, right? So you can add 9 and you can get to J directly.
yeah,
No, if CH is equal to A.
yeah, it will be at A already since it's equal.
At line 3, we make it as A, right?
Yeah, we are making it A. Yeah. Okay, so then if you are making no, if it's A, it will display what?
J, so add nine.
J.
Yeah, so we add 9.
But if it's false,
You just make.
Then
yeah. Because you're right. R0 is equal to A. So we add 9. You're right. Add R0 hash 9, and then
Add
0x21.
drag 0x21, and again it's done. It go to exit. Clear? Any question? But the other solution is like to another solution can have like you can have the ASCII value of J, and then you put it there, and then you load it up, you can display it. So this is another method. Okay, so today at this point of time now we are finished with the programming stuff. Now I'm going to the next chapter. Okay, so quiz 2 will be until lecture number 7. Okay, now we'll start with lecture number 8 now. So now we'll start with lecture number 8.
Fasil, the quiz is the rest of 5 until 7 or 6 and 7?
So basically the quiz will be only for programming, LCT programs, only LCT programs. I will give you okay, so this may be, I will give you a problem, all the problem, practice problem. It will not include any other thing. So maybe I will give you a C++ program, you need to convert it in this. Maybe I will give you a program and say, okay, what is the value of R0, what is the value of the analysis function. So it will be only relevant to LCT program, nothing more. Okay, so today I will start with a new topic of pipelining, and this is a very important topic. This is a very important topic. Please do not miss that. So what is a pipelining? It's a classic laundry example. Let's assume there are 4 people, A, B, C, and D. And each of these 4 people want to wash their clothes in a laundry. So there are 3 steps in the laundry process. Let's assume we have a washer, then we have a dryer, and then we have folding. Yeah, there are 3 steps. Okay. Now, so this is the task order. So this is A, B, C, and D. So let's assume A goes to the laundry. First he put his clothes in the washer. Okay. Then the next step, then he dries the cloth, and then he irons it. Okay. And then when should we start the process? At which time? How much time it will take to complete the process? 70 plus 20, 90 times, 90 minutes. It will take 90. Okay. Now, this is a sequential laundry. Now we start with washing, and then he dries the cloth, and then he irons it. Good approach or bad approach? Why?
Because as soon as the first person is done with washing, then
Yeah, he can start it. So basically, this is the typical sequential operation. This is the sequential operation. Now, this again. Now think. Please remember now. What I'm now going to have an analogy with the processor. Analogy with the processor. Remember, in the processor architecture, we have different phases of instruction execution. Should I rub this off? Remember, there are some instructions in manual. Let's assume this is I1, I2, I3, I4, I5. Okay. Let's assume I1 is in fetch stage. Okay, now what I'm going to do, so I'm having an I1, which is the black color. I1 is in instruction fetch stage, I1 in decode stage, I1 is in execute stage, I1 is in memory stage, and I1 is in the write back stage. There are 5 stages of an instruction execution. Remember, in the fetch stage, what will happen in the fetch stage? Program counter points to an instruction in memory. We will fetch the instruction. Where we will fetch it? Into IR. Clear? And in the instruction decode phase, we decode the instruction. In the instruction execute stage, we fetch the operand A and operand B, and we perform the arithmetic and the logical operation. In the memory stage, we do a load or store instruction. And in the write back stage, we store the value of a register. So there are 5 stages. Let's say now we have another instruction I2. And I2 start from here. Let's assume if we say instruction fetch stage, instruction decode stage, instruction execute stage, instruction memory stage, and instruction write back stage. So this execution is sequential or pipelined? Sequential. How many clock cycles it will take? 1, 2, 3, 4, 5. The first instruction will take 5 clock cycles, and also the second instruction will take 1, 2, 3, 4, 5. This is I1 and this is I2. So this is actually I1. And now this is what? Clear? And let's assume we have third instruction. I3, And then we have said instruction fetch stage, instruction decode stage, instruction execute stage, instruction memory stage, instruction write back stage. How many clock cycles will it take? Help me. If you do it sequentially, how many total clock cycles will be required? 15. Efficient approach or inefficient approach? Inefficient approach. Okay, now we will have an analogy between this example and this example. Okay, I will see. Now, it will take 6 hours. What we need to do? So basically, if we say, when A finishes with the washing, then we can start with the washer. And then, what we need to do? Then when A finishes with the drying process, we start the clear or not clear? So this approach, better approach, a good approach or bad approach? This one, the new approach, better. It means now we have saved a lot of time. Okay, now look into the instruction execution. Let's say we have 3 instructions. So now these are different clock cycles. So this clock cycle is 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and blah blah blah. Okay, now we have the first instruction. The first instruction in clock cycle 1, the first instruction is in which stage? First stage. Then it moves to which stage? Decode stage, execute stage, memory stage, and write back stage. Okay, now we look at the second instruction, I2. When I1 is finished with the first stage, so basically, what about I2? I1 is now free with the first stage. So what we can do? In clock cycle 2, can you see? In clock cycle 2, we can fetch which instruction? We can fetch the second instruction. And then in clock cycle 3, what we can do? We can decode it. Then instruction execution, instruction memory, and instruction write back. What will happen in clock cycle 3? Yes. When should we fetch? I3. In which clock cycle? 3. Then what? Instruction decode, instruction execute, instruction memory, and instruction. Okay, now if we have the sequential execution, how many clock cycles will be required? 15. And in this example, how many clock cycles will be required? No. 7. How many clock cycles have we saved? 8. So this is now the advantage of pipelining. I'll explain this one in another example. Let's assume Fatma and Sirija and Farah, Abdullah and Nojud, they want to get their Emirates ID. So there are different steps of Emirates ID. First, Fatma will go and she will take a token. When she will take a token, then she will go to the picture, they will have a picture, then she has to sign. So when Fatma take a token, she is free with the token, then Sirija can get a token instantly. Or should we wait for the Fatma to complete the whole process? Should we wait? No. So it means that now what we can do, so actually, if we have a sequential instruction execution, there will be more delay or less delay? More delay. And in a pipeline? Less delay. But there are some challenges with pipeline, and we will discuss some of these challenges later. What we do? We are overlapping. Pipelining is present in anywhere. It's doing the reports and blah blah blah. Okay, now, and please remember, this terminology is very important. Okay, now, the pipeline terminology. What is the latency? The latency is the time for an instruction to complete. The latency is the time for an instruction to complete. Okay, what is the latency of instruction in this example? What is the latency of any instruction in this example? 5 clocks. So in this case, latency for the time for an instruction to complete, so the latency of one instruction is what? 5 clock cycles in this example. I1 will take 5 clock cycles, I2 will take 5 clock cycles, and I3 will take also 5 clock cycles. Throughput. The number of instructions completed per second. Or we can also say how many instructions are completed per cycle. Okay. Now it means that how many instructions are completed per cycles here. So it means if you look at this example. No. Please, this is a little tricky. It means that how many instructions are now completed. So it means that here. Please remember now this is here 3 instructions are completed in how many clock cycles? Total clock cycles. 15 clock cycles. Okay? Now here in this example, how many instructions are completed? So it means that 3 instructions are completed in 7 cycles. Here the throughput is less. Here the throughput is more. So it means that more instructions are completed. So it means that now we can see here. So 3 instructions are completed in 7 clock cycles. So what is now the throughput? So 7 divided by 3. So 2.33. So 2.33 instructions are completed per cycles. Clear? So here the throughput is more and here the throughput is less. Clear? The clock cycle. Okay, now it means that the time duration of one clock step, every processor moves in a clock. So please remember, in your digital system design, we have some clock cycle. Remember? So we have the rising edge of the clock. In digital system design, we have flip-flop. Flip-flop can either be rising edge of flip-flop or falling edge of flip-flop. So if you have a flip-flop, so now this is actually flip-flop. So this is what? Clock cycle 1, and then clock cycle what? 2. So what is the clock cycle? Clock cycle is the duration of one clock period. And how can we compute the clock period? Yes. Clock period is what? 1 divided by what? 1 over frequency. If the frequency is bigger, like we have a bigger frequency, let's assume 1 gigahertz. So let's assume if the frequency is 1 gigahertz, so the clock period will be 1 divided by 1 gigahertz, which is actually 1 divided by 10 to the power 9, which is actually 10 to the power minus 9. So it will be 1 nanosecond. Clear? So the clock cycle is now inversely proportional to the frequency. If we have, okay, let's assume the frequency is 2 gigahertz. If the frequency is 2 gigahertz, so what will be the clock period? 1 divided by 2 gigahertz, 1 divided by 2 multiplied by 10 to the power 9, which is equal to 1 divided by 2 multiplied by 10 to the power minus 9, which is equal to 0.5. Clear or not clear? So let's assume this is my 1 gigahertz frequency. If this is 1 gigahertz frequency, so this duration will be how many clock cycles? Tell me. 1 nanosecond. And this duration will be what? 1 nanosecond. If we have 2 gigahertz frequency, so we have how many clock cycles here? So this is the first clock cycle and this is the second. So this is clock cycle 1 and clock cycle 2 and so forth. So what is the clock cycle? Clock cycle is inversely proportional to the frequency. If you have a higher frequency, then clock period will be smaller or bigger? Smaller. Any question? Okay, cycle per instruction. How many clock cycle it is taking per instruction? So in this case, how many clock cycles? So total 3 instructions are completed in 7 cycles. So it means that CPI, cycle per instruction. It means that there will be 7 cycles and there are 3 instructions. So this is it will take 2.33 cycles per instruction. And here 15 divided by 3. How many clock cycles per instruction? 5 clock cycles. Here we have more throughput, and here we have less throughput. How does pipelining work? Properties. All operation and data apply to the data in register typically change the entire register. Only load and store operation affect the memory. Okay, please remember. Now we have different stages. Okay, let's say if we want to fetch an instruction. We want to fetch an instruction. Who will point to the instruction? Remember my first and second lecture. Who will point to the instruction? PC. Remember? PC point to the instruction. And from PC, remember, if you remember, so it means that PC will go to MAR and then what will be in the MBR? The content of the memory location, the content of MAR. Remember? In IR, what will happen? In ID stage, IR will contain what? The content of MBR, and then we do go decode the instruction. And instruction execute stage, what will happen? We have op1 and op2, remember? ALU, and we did it, all these things. And then we have a memory stage. Please remember, memory stage is only required for which instruction? Help me. For load and what? Store. What are example of load in LC3? LD, LDR, and blah blah. And what is example of a store? ST and STR and blah blah blah. And in the write back stage, we store the value of a register. So which register are we storing? R what? RD or RS1 or RD? So RD will be overwritten into memory. RD will be overwritten. So how many stages are there? So I will give you an example. So let's say we have an add instruction. Add R3, R2, R1. First it will be fetched. Then the binary opcode of the add will go to IR. And that IR will have different fields. The opcode field, remember? Then which field? RS1, RD, RS1 and then what? RS2. And then op1 will contain what? The content of RS1. Op2 will contain the content of RS2. And then we have an ALU. And ALU will be op1 plus op2. The memory stage will not be used for the add instruction. And in the write back stage, which register we are overriding? R3. So R3 will be overwritten here, which is actually the RD. So there are, remember, so there are 5, and this you need to revise all of these lectures, my lecture 1 and lecture 2, because I know we will be doing a lot of repetition from there. We will be doing a lot of repetition. Clear? So please revise your lecture 1 and lecture 2. So we have 3 classes of instruction. What is the first instruction? Arithmetic and the logical unit. And even in the arithmetic and the logical unit, okay, what is an arithmetic instruction? Please remember, now we need to revise all this stuff. I'm not going to revise it. Please remember, in this thing we will revise it, at least you know go through all. What is an example of arithmetic instruction? Add. Not. In LCD. Okay, now even within arithmetic instruction, there are 2 types of instruction. R type and I type. Please remember, I type and I type. So please, that's the reason that you need to revise all these things. Then we have the logical instruction. What is the example of the logical instruction? And even in that, and there are 2 types, R type and I type. So we have the arithmetic and the logical instruction. Okay, the arithmetic and the logical instruction, please remember, will require the fetch stage, the decode stage, the execute stage, but the arithmetic and the logical instruction will not require mathematics stage. Clear or not clear? The load instruction, the load and the store instruction. The load in the store instruction will require which stage? The memory stage as well. But it will also require ALU stage. Why? Now, anyone. Why the load and store will require ALU? Anyone? No. Anyone? Anyone who will answer this question will get some points. Right?
Calculating the offset.
No. Yes?
Because the access memory.
No. Why? Because for the memory, yes. Now if you have the memory, basically we need to have a load instruction and a store instruction. But why the load and store instruction will require ALU? That's my question. No. No. Because we need to calculate the effective address. And to calculate the effective address, we need to add the content of the base register. And please remember that, because remember, think of the scenario. Let's say we have an LDR, R5, R2, #T. So actually, what is the effective address now? What will be the effective address here? Yes? R2 plus what? Plus 3. This will go in the ALU to what? Up 1. This 3 will go where? Up 2. And this will go and the sign extension. And we will do the sign extension now. And we need to add it. And that will give me the what? The effective address. And that effective address will go where? To ALU result. Yes or no? And from that ALU result, where it will go? No, where it will go? No! Because now we go to the memory stage. When we go to the memory stage, it will go where? MAR. You got it? Please remember, we will do a lot of tricks in my next lecture. So this is very important. So I want you to revise all of the stuff of lecture 1 and lecture 2. All the details are mentioned, and we will go into more and more details there. And then we have branch interrupt instruction. We will do it later on. So the arithmetic is the logical instruction, and the logical are add and or. Then we have the load instruction. Please remember, even in the load instruction, we have different things. We have the base register plus offset. So basically, this is what? In LDR, it's the base register, base plus offset. If we have LD and ST, please remember, and this may also be a question in an exam. Which of the instruction are PC relative? Which of the instruction are PC relative? Help me. LD and ST are PC relative. Which instruction are base plus offset? LDR and STR. So we need to calculate that. So in this case, please remember, this is what is, if you look at LDR and even you look into the data sheet, what is this thing? This is my R base. And this is my what? Offset. And this offset, please remember, this offset is what? Offset 6. Remember? This is offset 6. And if you have PC relative, let's assume if you have LD, that is PC relative. R9, R7, offset. This is offset what? Offset 9. This is PC relative. And if it is PC relative, so we also need to compute the effective address. How can we compute the effective address here? Help me. Incremented PC plus sign extension of the offset. Sign extension of the offset. And this incremented PC will go where? Help me. No. This will go to ALU. Op 1 plus op 2. This will go where? ALU result. And from ALU result, where will it go? MAR. And whatever is the value is go to MAR. Clear? So you need to revise all of this stuff. We have the branch, we will do it later on. So now this is the fetch stage, the decode stage, the execute stage, the memory stage, the write back stage, and the memory stage, and the write back stage. Okay, now please remember, what I'm going to do, so I will do this thing, and in the next next class is very, very important. Please remember, next class is very important. Very important. Now, if you look at here, how many stages are there? How many stages are there? How many stages of instruction execution are there? Which stage is this? Yes? Fetch. Which stage is this? Decode. Then? Execute. Then? Memory access. Then? Okay, now we will study each instruction one by one. How these instructions goes through the pipeline. And I will give this an example. So what I am going to do, I am going to write this out. And I am going to do it with an example. And this is very important. This I will give it to do it with an example. And just remember, this is very important. This is very important. And you know, I will also repeat it the same stuff in my next lecture. So this lecture is important. Okay, now think that we have an instruction, and that instruction is LDR. LDR R5 R2 H4. Clear? Assume that we have some R2. So now let's assume we have some R2. This is my memory. This is my memory. And let's assume this is R2. R2 values is 0x4000. So this will be some address 0x4000, 0x4001, 0x4002, 0x4003, 0x4004. Okay, R2 is pointing to this location. And please remember, whenever we are using LDR, so it means it can be used to access an element of an array. So let's assume this R2 is A0 now. This is the first element. A1 will be stored where? Here. And what will be stored here? A what? No. A4. The fifth element. A4 will be stored here. Okay, now let's assume we have the value of R5. And the initial value of R5 is 1111. What will be the new value of R5? Tell me. The new value of R5 will be A4. Am I right or not? Yes or no? Yes. Okay, now this is an LDR instruction. If this is an LDR instruction, this is a code section or data section? This is a code section or data section? Help me. Data. This is my data section. Now let's assume we have a code section here. And let's assume that address is 0x3000. And this 0300 will store LDR. What is the code for LDR? Can you remind me?
0110.
Yes, I think it's 6. So this is 6 opcode, then we have 6. So this is actually 6 R5 101 R2 010 and hash 4 1 2 3 4 5 6 7 8 9 10 6 bits. So 0000100. If you convert this into hexadecimal, so this will be what? 6 1010 8 8. Who will be pointing here? Help me. PC. Now think of the scenario. Think of the scenario. Now we are in the fetch stage. We are in which stage? Fetch stage. What will be the value of PC? Help me. So please remember, this is my instruction fetch stage. The value of PC will be 0x3000. Whenever we do the fetch stage, so this, please remember, this will go to where? What will be the MAR now? Help me. 3000. Clear? What will be in MBR? 0x 6 A 8. Read write bar. Yes. 1. And you can say read write bar, chip select, and you can do that. I'm not going through much detail at this point. Okay. Now, then we have the decode stage. So now please remember, this is in clock cycle 1. So now we have an LD, we have the instruction fetch stage. So in instruction fetch stage, we are now in clock cycle 1. And in that clock cycle 1, program counter is pointing to an instruction in memory. That instruction will be fetched. It will go to MAR, this will go, and this will go to MBR and blah, blah. Then we have, what is the next stage? Tell me. Decode stage. And in decode stage, so now we have clock cycle 2. So in general cases, so now you can see the program counter will that, and it will go to the instruction register. It will go to the instruction register. So it means that now, in what will be in the instruction register? So in instruction register will now contain the content of the memory of MAR. So the content of IR will be MBR. And in instruction decode stage, clock cycle 2, we will now decode the instruction. So basically, in the decoding stage, so now IR will contain the content of MBR. And what will be the content of IR? Help me. 6A what? 6A. Now we will decode this instruction. We'll okay, now I think so. IR will be the content of MBR. So IR will be the content of MBR. So IR will now content of MBR. Because can you see IR is in the first stage. So in IR will now contain, so the content of IR will be 6A. Clear or not clear? Now, we go to clock cycle 2. So now we are in the decode stage now. We are in the decode stage. If you go to the decode stage, we need to load which register? A and B. So these are, so we need to load A and B. Okay, now in here, what will go to A? In A, what will go? It will go, now please remember, which instruction are we studying? We are studying decode, but which instruction are studying? LDR. So this instruction, LDR, RD, in general, please remember, RD, then what? Help me. R base. What is R base here? R2. R2 is my R base. This is my R base. What is this thingy? RD. What is this thing? Offset. Now we are in the instruction decode stage. What will be A? So please remember, in this case, if it is LDR instruction, so A will now contain the value of R base. And what is now the content of A? Help me. R2. And what is now the content of R2? For this example. Yes, 4000. Any question? Okay, now in the decode stage, we will load into B. But here in B, we will do the sign extension of the offset. What is my offset here now? #4. So if the sign extension of R4, so B will be what? For LDR, it will be actually the sign extension of offset. And what will be now the value of B here in this example? 4. #4. Clear or not clear? So in decode instruction, we fetch the operand and load operand A and B. Okay, now, no. B is coming from register file. So we don't care. So please, B will be don't care. B will be don't care. Now we have this immediate field. So the immediate field, what is now the immediate field? Help me. 4. Now with this instruction goes to, okay, now what is the first stage? Fetch stage. What is the second stage? Decode stage. What is now the next stage? Execution. So now we go to the execute stage now. And because it's an execute stage, we need to compute the effective address. So for this, we need to compute the effective address. And how the effective address will be computed? So the effective address will be actually R base plus sign extension of the offset. But this RBS is now where? A. And plus sign extension of the offset is now in immediate field. But in the execute stage, please look at here. Now we have two muxes. Here, A will pass here. So if we have mux here, so this is, okay, now we have mux here. Please remember this is important. Now we have mux here. And this is the select line of the first mux, cell A. And then now we have the second mux. We have cell B. This is 0 and this is 1. This is 0 and this is 1. If you look at here, what is coming from here? NPC. Okay, ignore about NPC here. What is coming from here in the second case? A. If you look at here, what is coming from here? B. And in the second case, what is coming from here? The immediate field. So now please remember, since we have calculated the immediate field, so immediate field will go from here to here. What is the value of cell B? It will be 1. Got it or not got it? And then, what do we need to pass from here? NPC or A? A. So A will pass from here. What is the value of A? Now this is important. What is the value of A in this example? What is the value of immediate? 4. Now this is an ALU. We need to compute the effector address. We need to add it. What is my effector address? Yes? 0x what? Am I right or not? Now we have calculated the effector address. Now, what will be my next stage? Tell me, what will be the next stage? This stage.
Shouldn't be 4004.
Which one? Yes, 40004. Yes. What should be the next stage? Memory. And please remember, in the memory stage, we need MAR and MBR. Okay, this effector address will go where? And MAR. What will be the value of MAR? Help me. Okay. Are we loading or are we storing? Loading. Read operation or write operation? Huh? Read. Read write bar will be what? 1. No. Because read is active high. Read write bar is 1. If I put a static here, is 0. Okay, now read write bar. So now we are reading MBR. Okay, now we are going to this location, 4004. What will go to MBR in this case? So the content of MBR will be what? Help me. A4. So here we have the MAR, we have the MBR. Now we have the memory stage. And what is now the last stage? Write back. Okay, now in the write back stage, which field will be used? RD. So what is RD here? R5. So R5 will be overwritten with the value of what? MBR. And what is there in MBR? A4. And then R5 will now, okay, now when we are writing, okay, which register are we writing? That destination, and then it's hard. So now in my next lecture, we will study many instructions and how it will go through the pipelining stage. It's all for today. Thank you.